Hi, my name is Efthimis, and I would like to present our work M3, Multimodal Masking Applied in Sentiment Analysis, which is a joint work with Georgios Paraskevopoulos and Professor Alexandros Potamianos at the National Technical University of Athens and Athena Research Center. So, when training multimodal networks, we would intuitively expect them to match and even surpass the performance of their unimodal counterparts. However, this is not always the case. There are scenarios where unimodal networks match and even outperform multimodal ones. The reason for this somehow counterintuitive behavior is attributed, there are two reasons. The first is the different generalization rates of the various modalities, which means that some modalities learn faster or easier than others. The second is the heavy overparameterization, which exists in most of the multimodal architectures. In the sentiment analysis paradigm now, although the speech modality is assumed to be the most informative one, text is usually more robust, and therefore text-based models perform better in the sentiment analysis tasks. So this results in models that tend to over-rely to that particular modality in order to make a correct prediction. Ideally, we would like all modalities to contribute as much as possible. This means that we would like to exploit all the complementary information across modalities and better capture cross-modal interactions across modalities. However, most of current research is mainly focused on building better multimodal architectures and better fusion mechanisms. So a natural question is, could we try to use all the available information by directly battling this over-reliance over particular or over some more dominant modalities? So M3 aims to take a step towards that direction by introducing a layer that can be applied at any architecture without any further modifications and without any additional learnable parameters. So let us now describe how we're going to, the rough idea. Let us consider this simple example in which we assume that the text modality in the red box is considered to be the dominant one. When we say dominant, we mean that models tend to over-rely to that particular modality in order to make a correct prediction. So the idea here is to mask that modality and force the network to make a prediction in the absence of that dominant modality. We believe that this will force the network to better exploit information in other modalities and further better capture cross-modal interactions. So once again, the idea here is to mask the dominant modalities during training in order to force the network better exploit information that exists in other modalities. So, taking this idea one step further, we introduce M3. M3 stands for multimodal masking. M3 is a layer that takes as input a multimodal sequence and randomly masks a modality at every time step of that sequence during the training procedure. So, we believe that applying M3 during the learning process directly battles over-reliance because it forces the network to make a correct prediction in the absence of some randomly chosen modalities, and therefore it exploits the complementary information across modalities better. We will now describe how M3 works. We have introduced a set of hyperparameters in order to control its operation. The first is the probability of masking at the current time step. This hyperparameter controls whether we're going to mask or not at the current time step. We've also introduced an additional set of hyperparameters which offers a more, let's say, fine-grained control over which of the involved modalities are going to be masked. In our experiments, since we have three modalities, text, audio, and vision, we have introduced three hyperparameters: the text masking rate, the audio masking rate, and the vision masking rate. And we also note here that these three probabilities have to sum to 1. So let us describe how M3 works in the toy example. We're given this multimodal sequence of 3 time steps. So M3 will decide at every time step whether it is going to mask or not. If it decides to mask, then it is going to further decide which of the involved modalities is going to be masked. So, at the first time step, M3 decides to mask and mask the central modality. At the second time step, it decides that it should mask a modality, and that time it masks the leftmost modality. And at the final time step, it says that no modality should be masked, and therefore, for that particular time step, all three modalities are available during the training process. This procedure is repeated for all time steps and for all the samples in our batch. For our experiments, we have used the SimView Mosaic dataset. It is a large database for sentiment analysis. It consists of YouTube video clips of people telling their opinion about some movies. So it's essentially a multimodal movie review dataset. Its video segments are annotated by humans in a scale from -3 to +3, where -3 indicates the strongly negative sentiment and +3 indicates the strongly positive sentiment. SimView is publicly available under that link. So we now introduce our baseline model. As illustrated in the figure, it consists of two subnetworks. The first one is responsible for extracting unimodal representations, unimodal encodings. We have used some bidirectional LSTM with self-attention mechanism, and as illustrated in the figure, we have used a separate encoder for each one of the involved modalities. The output of that first subnetwork is the representation for text, the audio, and the video, namely MT, MA, and MV. The second subnetwork is responsible for capturing cross-modal interactions and also performing the final prediction. We have used some cross-modal attention mechanism, which are inspired by the Wilbert architecture. And in this network, we capture text-audio interaction, text-video, audio-visual, and also a trimodal representation between the text modality and the audio-visual. All the available representations, both unimodal and multimodal, are concatenated and fed to a bidirectional LSTM, which performs the final prediction. During our experiments, the M3 layer is inserted directly between those two subnetworks. So, let us now see the results of our experiments. First of all, we compare ourselves to the current state of the art. We compare ourselves to some strong baselines, such as MULT, which is a transformer-based architecture. We also achieve state-of-the-art results, which indicates the efficacy of our approach. And what I would like to note here is that our results in that table are averaged over over five independent runs. So, another experiment we carried out was to perform an ablation study in order to find which is the best masking strategy. In those figures, I would like to note that the black dots indicate feature values, like 2, 3, or whatever, and gray dots indicate masked feature values, which are considered to be 0. So we consider this 4 different masking scenarios. The first is the baseline, where no masking is applied at all. The second is random masking, where we randomly mask some features from all 3 modalities. This somehow may also resemble dropout, but we do not perform the rescaling trick that dropout uses. Here is a softer version of M3, in which we randomly pick a modality at every time step of the multimodal sequence, but we only mask a part of that particular modality, a random part of that particular modality. And of course, M3, in which we randomly pick a modality at every time step and we mask all the features from that particular modality. So, the results from that experiment are shown in this table. We have used the 4 masking schemes which we described in the previous slide, namely the baseline, the random masking, the softer version of M3 and M3. And our results show that M3 consistently outperforms all other masking schemes, which means that M3 is the best masking strategy, at least for the sentiment analysis task. What we also found interesting during this experiment is that the softer version of M3 does not always outperform random masking. This result indicates that we have to go all the way through and mask all the features of a particular modality in order to gain the maximal gain in performance. This result also highlights an alternative viewpoint for M3, which is that it can be seen as a form of structured masking. So, in our last experiment, we considered the different text masking. We considered different text masking rates. So, we simulated two scenarios. In the first scenario, all three modalities have equal probability of being masked, namely 0.33. In the second scenario, we used a more aggressive text masking strategy, and therefore we used the value of 0.60 for the probability of masking at a text modality. We remind here that the probability of masking the text modality is denoted as pi with index capital T, and the probability of masking at every time step as P with index capital M. So, our results can be seen in this table. We used 4 different values for the probability of masking at every time step. So, what we see from this table are the following. First of all, the best value for the probability of masking at every time step is consistently 0.20 and 0.25 for both scenarios. Both the scenario where all modalities have equal probability of being masked out, and the scenario where we more aggressively mask the text modality. What we also note here is that regardless of the hyperparameter choice, we have a relatively good performance, which almost always outperforms the baseline models, which means that our layer does not, we do not have to tune, to exhaustively search in order to tune our layer. Finally, the most interesting result, in my opinion, is that in the second scenario, larger text masking rates result on better models on average. This is very interesting because it experimentally verifies our intuition that more aggressive masking of the dominant modality, of the text modality, results on better solutions on average. So, to conclude, we've introduced M3, which is a layer that can be applied at any multimodal network without any architectural modifications and without any additional learnable parameters. We've experimentally verified that it boosts performance when applied during the training procedure compared to the baseline model. And our intuition on why M3 works is that it forces the network to make a correct prediction in the absence of some randomly chosen or some more dominant modalities. In the future, we plan to apply M3 at different architectures, such as transformers, which are considered to be state-of-the-art in many tasks. We also plan to apply M3 at different multimodal setups, such as audiovisual ASR and visual question answering. Another line of research is to try to schedule the individual modality masking rates in order to better control the different generalization rates across modalities, which is considered to be a major issue when training multimodal architectures. And finally, we plan to investigate the robustness of networks trained with M3 versus networks trained without M3. Our code is publicly available under this GitHub link, and you can feel free to contact me for any questions regarding our work. Thank you.
This is the final presentation in this session, so we will have some time for questions. If there are questions from the room, please come forward.
Thank you very much for the presentation. I was just wondering, do you plan to also extend your work to making informed decisions when you pick the probability of masking a certain modality? I guess there's also characteristics of the text over speech that would make the probability maybe vary. Meaning that you could change that probability over time. For example, pre-training a model like a text classifier, trying to see what performance the model gets by doing that prediction, and then looking at which modality you should mask because it looks easier to make the prediction via the text classifier, for example. Yeah, just this kind
So you mean, let me see if I get it correctly. You mean that you have to somehow figure out which of the involved modalities is contributing more to the prediction and mask that modality?
Yes, somehow removing the fact that you rely on the
on randomness.
On random values, or just the fact that you hard code the hyperparameter of the probability to mask text and just make that depend on the text characteristics.
I plan to schedule the different modality raised, but the first naive thought is to schedule it in a way that it does not take into account which of the involved modalities, in particular for every sample, is contributing more. That would be very interesting, but you have to find out. You have to have a tool which will inform you which of the involved modalities is contributing more. That's why you use random or semi-random criteria, because it's not obvious, at least to me, how to figure out which of the involved modalities is contributing more for a particular prediction. We know that the text contributes more. The text-based models perform better for the sentiment analysis task, but you can know I don't know how you can know for sure for a particular sample or a batch of samples.
What I had in mind there would be eventually to fine-tune a text classifier, fine-tune a speech classifier, just based on those modalities on the same training data initially, and then on a subset of the training data.
You can figure out in which samples are misclassified by each classifier, for example.
Yes, and then if you see that the text has 99% performance, for example, then you could just discard that as being the dominant.
Yes, that would be very interesting.
It was just a...
Yes, that would be very interesting. Thank you.
So we have a question from online, from John Kane. I might have missed it, but did you evaluate applying this mode level dropout at interference time? Do you think that the approach might improve the robustness if one of the models is missing or unreliable?
Can you please repeat
again? Did you evaluate applying this mode level dropout at interference time? Do you think that the approach might improve the robustness if one of the models is missing or unreliable?
Okay, now. We used M3 only during training. The M3 layer is switched off during inference. I cannot say for sure, because I haven't experimental results, whether it's going to help. I believe that it's one of our future plans to investigate whether it really helps the network in cases of missing modalities, and that was my last bullet in our future work, that we're going to plan to investigate the robustness of models trained with M3 versus models trained without the M3 layer.
Is there another question from the room? Okay, we do have one more online from Piero Pierucci. They said, are you envisioning extending or evaluating M3 for UNA versus multimodal emotion detection tasks?
For emotion detection tasks?
Yes, for UNA versus multimodal emotion detection tasks.
At the moment, no. We are planning to apply at maybe audiovisual ASR setups and maybe some visual question answering, or what I would like to do is apply it in scenarios where there are more than 3 modalities involved, in order to make it more challenging for the network and find and further investigate its usage and Well, that's it.
And I guess this will be our final question, maybe. Siyuan Zhang says, nice work. Do you think this mask could be learnable and potentially the network could make decisions by certain percentage of each unimodal information on its own?
Yeah, that's very interesting. To have a learnable mask. The only experimental result we have so far is that the ablation study we performed, in which we showed that we have to mask the whole modality in order to gain the best results. Masking some features does not always work, which was the softer version of M3 in our experiments. However, the idea of learnable mask is very interesting, which of course comes at the cost of adding learnable parameters, which in this work at least we did not want to add any additional learnable parameters. And was there a second part of?
No, I think that was it. Yeah.
Okay.
Okay. So that concludes this session. Let's give our speaker a round of applause.